So here's the agenda for our session. I'm going to kick us off with a few thoughts on subjective versus quantitative co-design. We're going to be followed by Anne with a talk on enabling application and system data fusion, followed by Haya and Richard and Bill, and we'll conclude with a moderated discussion by David. And hopefully we'll have at least 30 minutes for that moderated discussion, and folks in the audience will be able to jump in there and really add some good content, and we'll try to capture everything. And so with that, let me go ahead and get started with the first presentation. Let's see. Oh, interesting. I just have to hit click. All right. So the title for my talk is Thoughts on Subjective versus Quantitative Co-Design. I'm Terry Jones from Oak Ridge National Laboratory. And the outline of my talk is as follows. I'm going to begin by really just kind of starting off the session with a little bit of context for what we're talking about here in general, and a little bit of background on it, and why I think it's such an interesting topic. And then we'll spend the bulk of this short presentation on how it affects ECP and ECP's people. And then I'll just go ahead and conclude with some events to be aware of. So quantitative co-design, monitoring, what is all this about? And whenever I think about it, I like to go back to around 20 years ago and reflect on how things have changed. That helps me to put the topic in context and in particular, underscore the importance of the topic. And so, if you go back 20 years ago, we were talking about teraflops back then. And, I'm going to give this presentation from the viewpoint of someone that's in facilities planning. So in other words, you've got $75 million in your pocket, and headquarters is asking you to decide which machine from a handful of different vendors you need to bring in to really advance science. And so that's your task, and you're looking at doing that successfully. How did you do that? Well, back in the day, we had all these rules of thumb. We had all these little conventions and fallbacks, to where here's the intuition. Let's start with how many floating point operations we have per second in this machine, and then based on that, we'll have a rule of thumb on what that means in terms of how big the memory should be. And then once we decide the memory, we can decide how big the disk space should be for that node, and how big the disk space should be shared for the parallel file system. And then beyond that, we can do the rest of the machine. And so there was all these little rules of thumb that came into play on the machines that you purchased. And I'm not trying to say that there wasn't any hard data that went into the design of the next machine or whatever, but it was heavily influenced by the folklore in the industry and the expert down the hall's gut on, well, we really should pay attention to this. And so whenever it came time to do the inevitable trade-off of, well, for this $5 million, should we bump up the CPU horsepower, or should we bump up the interconnect speed, or should we address latency in the interconnect, or maybe we need a faster parallel file system, or a bigger parallel file system. All these kinds of trade-offs, it was really hard to make the decisions. Looking at the workload, it was hard to know really which way to go. We had to go with all these intuitions. And so, well, how did that play out? Well, if you looked at ASCII Red, which went into 1997, back then, we used these little Kvyat graphs, and we had the notion of a balanced machine. And so, you could picture a balanced machine filled out the Kvyat graph in a circle. And so we would struggle to spec out a machine that was balanced. And as we move forward from ASCII red to the ASCII blue machine in 98, it had a little bit different shape, and we're carefully looking at these shapes and trying to come up with the balanced machine and following the rules of thumb. And so, well, what's the problem with this whole background? Well, I would say, I would liken it a little bit to if you're driving a car, and the rule of thumb is, well, for this car, a full tank of gas will give me about 350 miles. And so that's fine in most situations, but if you're driving through that famous stretch of highway in Southern California through the desert and there's no gas stations, you need to know, is it 331 miles or 364 miles? The rule of thumb really begins to get squishy, and there's implications. And so I would argue, that this topic is important because of if we have to go with rules of thumb, we're leaving science on the table. Not only for the design of which machine do we get next, and there's other topics as we'll get further in my talk that I'll mention, but we have such an important mission before us. We've heard this week of how important ECP was to bringing solutions more quickly for vaccination, for COVID vaccinations. And there's a world of things that supercomputing at our DOE centers are doing. And so if we leaving the tiniest bit of performance on the table, there's large implications of that, just like driving the car in the desert. And so back then, 20 years ago, if you would have told me, okay, look past petascale, look on to exascale, how are things going to be? What's your speculation on how things are going to be? I would have guessed that, well, things are going to be very data driven. We're going to have data on all these applications. We're going to get away from Joe down the hall and his intuition on what this variance is about or whatever. We're going to have all the data, associated with workflows and with the machines and the networks, and we'll be able to get down to the bottom of issues and so forth. And so that would have been my guess. But well, what's the reality? And so this is an actual table, that's talking about the exascale era, and you'll notice that, well, we haven't gotten away from these rules of thumb, these intuitions of what a good machine looks like, and I really think that there's a cost to that. Now, certainly there's a cost to monitoring and getting all the data too, and we need to talk about that. But I think that the conversation that we need to have is, what's the better way to go here? Should we continue moving on with intuition, or is it time to really figure out how to get past the tough barriers to make things more data driven? And so what are some of the problems with rules of thumb? Well, you're not able to really handle variance and outliers well, and that could, because forwarding our science is so important, who knows how a little issue could play out to society. Often close isn't good enough. Everyone's aware of nonlinear systems and phase changes, how you can go from 33 to 32 degrees, and there's a change in water, even though that there was a small change in the temperature there Fahrenheit wise. Another issue with rule of thumb is if it's based on someone's gut intuition, what happens when that expert's no longer available? And for national laboratories, where I sit, I feel it really reduces, again, this part of the talk is talking about from a facilities planner point of view. It really reduces the ability of us to give consistent guidance to the vendors on, what's important. When we start to really get down to making the trade-offs, do I want to to add 25% memory to this machine, or do I want to add 75% better latency to this interconnect? If I could do either one, what trade-off do I make there? We need to be able to do consistent guidance that's well understood. And for the vendors, it reduces their ability to make firm R&D trade-offs on product direction. So, we really need to, I think, find a way to get to where we have a data-driven environment in our supercomputer centers. There's just such benefit. And it's not only, I've talked about this from the facilities planner story, but there's a whole, in any supercomputer center, there's a whole zoo of different communities. And, system administrators need data-driven information for diagnostics and the current state resolution of the machine. The cyber and networking community, they need hard data about breach attempts and diagnostics in current state. People that are developing applications, they need hard data to figure out how to map their application to a particular machine as these machines are getting more complicated with more aspects. And also to get to the bottom of bugs and to understand variance and runs from run to run. I sat over in the computer science and math part of the labs, and in a lot of ways we're like the applications people, but we're specialists developing tools and libraries. And I'd say the same thing that applications people face, we face as well. And then there's a different community of operations people that, these people are looking at the electrical draw and the chillers. They need hard data as well. All of these different communities, I would argue, tremendously would benefit from moving more toward a data-driven environment where we can get we can go from maybe 95% to 100%, or maybe we're less, maybe we're at 80%. Who knows? If we don't have the hard data to say, but we need to squeeze out the availability because of the importance of the mission. And so if you only remember one part of my talk, here's the thing I want you to remember is this sentiment here is, without a knowledge, oops, how did that go forward? Hold on, I don't know what happened there. Without a knowledge of history, we're doomed to repeat the mistakes of the past. And without quantitative-based actions, we're doomed to the limits of our rules of thumb. And that's not where we want to be. So I'm going to start to wrap up the talk here, and we'll move on to Ann. But there are some events in this general area which I've hopefully convinced you that there's some meat here. There's something about this topic that could really advance not only ECP but supercomputing in general, but certainly ECP. So here's some events. I really want to plug this first event. I'm one of the organizers on this event, so I need to plug it. But the first International Symposium on Quantitative Co-Design for Supercomputers is going to be held during SC21. So stop into that. Here's some other events that I think are high quality events that address this very topic in communities throughout the world. And lastly, there are some potentials for some funding out in the wings. There's the potential maybe for some ECP contingency funds to facilities. So you'd want to talk to your facilities folks and see, is there a way you can work with them to improve things for an ECP perspective. And also there's a potential for an Oscar solicitation. I don't understand how every now and then my thing is changing screens. I was saying that there's another possibility for funding, the Oscar Reimagining Co-Design solicitation. At this point, they've had a workshop, and so that could very well turn into a solicitation. So watch for that. It would be with Hal Finkel. And so with that, I'm going to stop sharing. And for questions here, I'd like for you to just defer any questions on my things to the open session at the end with Dave. Anne is ready to go forward here. So Anne?
Okay, is it, can you see that? Is that all right if I do this in this mode?
Yes.
Okay, thank you. I am Anne Gentili from Sandia National Labs. I am going to be presenting work on behalf of a team of about 25 people that is about enabling application and system data fusion. So the motivation for this work is answering these key operational questions, which of course we are all trying to answer, right? For instance, if there is performance variation, is that due to system conditions or is that due to code changes? How can operations know if there are issues on the system? How can they know that applications are having performance issues when they don't know how the applications are supposed to be performing? And of course, what are the architectural requirements, for our next generation systems based on the site's workloads? All of these questions require us to understand together system data and application data. And, traditionally, these have been very diverse areas, right? There are people who, monitoring is seen as a system collection done by these people, and application profiling is done, only for certain applications and certain instances by these other people. But what we really need to do is fuse our system and application data together. And by that data, I mean measurements. So system measurements are things like IO utilization, CPU utilization, are components degrading, is there contention for the network? These are the kinds of things that we can get from system measurements. From applications, we can get measurements like, how is it progressing? What is the time per some, meaningful thing like a time step? What is the application even doing? What is it even calling? And if we can fuse this data together, we can start to answer questions such as, when we see an application's progress change, is that associated with a simultaneous change in resource state, right? If we see load imbalance in an application, can we get something that will let us think about root causes because we can see also inconsistent utilization in CPU or memory? There are many questions like these, and if we can answer the questions that help us understand application behaviors, then we can answer the questions that can help us improve our operations. So in order to do this team of people is building an architecture for continuous runtime fused system and application data, and also the associated analytics. So this is a high-level diagram. So on the system itself, we are collecting system data via Ldms. It has a high performance transport to get that data to where we're going to do analytics. We want to leverage that high performance transport by also using it to transport application metrics at the same time. And I will describe in a bit that we're getting those via COCOS. This combined data that is time-stamped so that we can see what is happening at the same time all goes into a high-performance database where we do continuous analysis, and at this point are targeting a dashboard where we will see something like, for instance, this blue curve is, what is the application performance, whatever that means, right? What is the system performance, whatever that means? And can we see features that that let us understand, can we then do some attribution? Can we then do some understanding? The application is behaving in this way because, right, it's using the system in this other way. So this is the architecture which we are building, and I'm going to go into a little more detail on that. So as I said, LDMS is what we are using for our system data collection, and it was designed to get low overhead, lots of data from the system, and support runtime analysis and feedback. Features of LDMS that are of interest are the transport is low overhead. So it is RDMA based versus like typical message bus things, which are IP based, right? The nature of system data collection is typically synchronous. So we want to get all the data from the whole system at the same time so that we can get snapshots into the system so that we can understand it holistically, right? We know what's going on across the system all at the same time. And we would get that at regular intervals because it's across the whole thing. We use for that data a structured data format, which is designed to minimize data movement. And in order to minimize the impact to the application on the nodes, we typically use a pull-based mechanism. So the entity downstream that's going to get the data pulls it from the nodes. And that means, right, all that machinery about timing of the pull, how you do the pull, is ensuring that, you know, you're still connected. All of that burden is off the node. So it minimizes the impact to the application on the node. There is a push-based one for structured data, but that's, you know, that's not the one that is mainly used for production monitoring. So that's how we do system monitoring with LDMS. We want to leverage the transport now for this other type of data. The application data instead is asynchronous data, right? It's some, you know, an event occurs not at a regular interval. It's not going to be structured because who knows how you would represent that event, whether it's different types of log messages, scheduler data, or in this case, you know, application events. And so we also have another capability that supports on-demand publication of loosely formatted information. So that's the part of LDMS that we're going to leverage for the application data. Application data, we are getting into this via COCOS. So I'm going to explain this at a high level. Luckily, we have a COCOS authority on the line who can answer any of your architectural questions. But at a high level, it's this, right? So when you write your application, you know, it is a lot to expect an application developer to write, you know, to design this for the various different types of hardware upon which it may run. So instead, right, the application developer can call COCOS's implementation of some function. COCOS has the designed version of that implementation for, you know, is it GPU based or CPU based or whatever, right? And that's the actual implementation of the code. And because it's got the implementation, right, of that functionality, it can also have timing data, profiling data within it. So right now, this COCOS functionality is loaded dynamically. So therefore, there's no recompilation necessary, right, if you want to use COCOS and also have timing data. It conceptually has things like hook points for here are kernels or here are regions, right? Here are concepts that are of interest. And as I said, it has profiling within it. So there's already some known what kinds of measurements would we want. So the user doesn't have to specify it. So we're going to leverage those aspects of COCOS and then take that data, shove it into this COCOS LDMS connector, which publishes via the Streams API to the LDMS transport. So COCOS is dynamically injecting into the LDMS stream versus that push-based functionality that I mentioned before. Now you can always get, you know, you can get an infinite amount of application information. So if we need to make some decisions about, you know, what is the most important information, or, you know, what rate of data can we handle, the team has developed it's called a COCOS sampler. Don't be confused with an LDMS sampler, that keeps statistics and timing information to determine what and when we're going to publish. So right now, you know, things are, you know, you could push it all, you could push it every so often, you could push it maybe, you know, every n executions of something. So that's how we're getting the data in. And now this is the configuration that we are targeting first. So Eclipse is our CTS1 system. It has 1,500 nodes. Empire is our targeted application. Its layout is, you know, when it's laid out by the developers, they run 1 rank per socket. So on Eclipse, there's 2 sockets per node. So what we are doing is 1 rank per socket, right? 2 ranks per nodes then are going to be shoving application data into the concurrent LDMS stream that is also getting the system data. And the application data rate that we are targeting is the following. The ranks will publish 1 time per 10 milliseconds. And what they're publishing is going to be something on the order of 1,000 multi-part data values. So that could be, for instance, you know, triads of, right, this kernel has been called this many times, you know, for this duration of time, right? So a rank will publish this multi-part information every 10 milliseconds. So just so it is a somewhat rich, right, set of data, but you know, so it can express something more than the 10 milliseconds, right? It's not one thing per 10, you know, only 1 data value per 10 milliseconds. It is a rich 1,000, right? I'll talk about the format in a minute, and I will talk about the store, but that's what we're seeking to support. So for analysis and visualization, the goal then is to get a fused view of the system and application performance together based on this data and subsequent analytics. So things like, you know, we've all done the system visualizations that are time series, but what does that look like when it's in conjunction with, for instance, right, how long are the time steps taking? How many functions are being called per second? And we're supporting this by the following architecture. So the LDMS data goes into a database. The database that we are chosen was specifically designed because it is distributed, and it also supports being able to access the data via Python queries with minimal recopying of the data. So we can be doing continuous Python-based analysis on the database. We can also, and that can propagate up to the display. You can also, from the display, do queries that again call the analysis, and therefore you only have to do the analysis and access that part of the data that is in the display. So you don't necessarily have to do analysis over the full database. Okay, so where are we on this, right? You know, our goal is to get unprecedented runtime insight into performance and resource utilization features. There are a number of challenges, right? So that format that's coming from Cocos, right? We've got to parse all that data. It's not as frequent as, you know, typical profiling data, but it's still fairly frequent. How do we support the ingest rate in the database? Again, toward that thing about the fidelity of the data collection, right? What features can we actually expect to resolve from applications that are sort of that 100 millisecond to a few seconds, right? So we're not getting, you know, we're not getting the typical fidelity of a profiler. So what meaningful things can we see in the application on those timescales? What even are the meaningful data and events of interest? How can we build these visualizations together, right? It's high fidelity data. How do you reduce the dimensionality so it's meaningful when you look at it? And what are the analytics? To this end, we are just about on the verge. We're going to have our first large scale data set from this, from some 24-hour code runs that are going to be run on 300 nodes of this system. So we're going to collect these data and start targeting, right, some of these analysis and visualization questions. Thank you. Sorry, I ran a bit over.
Great. Thanks for that talk, Ann. That was great. Let's move on to Haya for the next talk.
All right, I'll go ahead and share my screen. Can you see my screen and hear my voice?
Yes.
Anyone? Okay. All righty. Great, let me put this into full screen mode. So Yep, I'm Hei-Nam from Los Alamos National Lab, and I was invited to this session to provide the application viewpoint for monitoring, and so hopefully I can provide that a good view of kind of what are the challenges for applications people. I do have a little bit more insight in that, I typically walk with the system from cradle to grave, where I'm there during acceptance and then also, part of the production line. So get to see all the fun challenges. And I wanted to share with you kind of, I would say, a weekly challenge that happens where we play HPC Clue, and usually there's some sort of application failure or performance or some anomaly happening weekly. And so we definitely would love to get this unprecedented monitoring capability, because it takes a long time to play HPC Clue every week. And because we're so OCD, we just keep doing it. It takes up a lot of our time. So HPC Clue, if you are as old as I am or older, you know the classic game of Clue where you have to determine who murdered the game's victim and where did the crime take place and which weapon was used. And you're supposed to go around from room to room answering, getting information from different players, strategically moving around the mansion, collecting clues to understand, to figure out what were the circumstances of the murder. There are 6 suspects, 9 rooms, 6 weapons. We're talking about a few hundred possible scenarios. It was a fun game, but it reminds me of the game we play every week. And I have to stress, every week someone is coming to tell me, have you seen this before? And then I'll go down a rabbit hole. So in HPC Clue, there's way more players. There's way more, weapons, more rooms, thinking about power, cooling, backplane, rectifier. I mean, there's so many components in our new systems that are coming into play. CPU, GPU, memory, network, IO, system software, programming environment. This is just a small set of the, the components, and it leads to thousands of possible failure root cause scenarios. You see an error message, but that's just the spew. That's not necessarily the root cause. And then on top of that, in HPC Clue, the error messages are really cryptic and they're changing from system to system. So we can't depend on, being able to deduce things from system to system. Some rooms are locked because I'm not root. So I can't find the information that I need to actually find the root cause. Some events only happen at large scale, and then trying to get, debug runs at large scale are really challenging. Plus, we're also causing problems too, because the application is also under active development. It's a moving target. And then on top of that, I think what we're seeing more and more nowadays is that this interaction is not from one root cause, but kind of a interaction of multiple components that cascade. And so it really is more and more challenging to play HPC Clue and more time consuming. On top of that, we also do silly things like not reading the documentation. So we're in that the scenario as well. And so we would love to have unprecedented monitoring capabilities to help us solve these puzzling application mysteries that are hindering our simulation throughput through each phase of the system lifecycle. So as we think about monitoring, I also want you to think that, the system is not static in terms of what it's, in terms of the monitoring that's needed, because each phase of the lifecycle brings out different kinds of questions that we need to, to solve. So starting from acceptance, even trying to incorporate new system log type information. What does this error message even mean? Comes in through acceptance. And I want to just put in a plug for the box that Oscar ran this morning with a variety of other facilities folks on V&V at the facilities and doing acceptance testing. And so I think that there's a lot of great tests in there that could go into the acceptance and monitoring components. So there's acceptance in the early user period. We're first putting our applications onto new hardware. Why is my application crashing? only when running on KNL and not all of these other node architectures? Why is my application crashing at certain scales? Why is it only crashing when I'm using threading and not MPI only? There's so many just mysteries about how our applications interact with the system early on and at large scale. And then we have a different set of kind of monitoring that we do once the system is in production. Actually, a lot of our applications, especially at LANL, have some sort of nightly regression so that we're watching the performance of our code over time. But still, even with that, there's still a lot of questions that come up, like, why is my performance degrading? That's not going to show up in timers that we're putting into our codes. Or why is my regression test diffing now and I didn't do anything to change it? Or do I have a bad node and I'm getting a wrong answer? Do I have a degraded node and that's why my performance is, impacted? Did something change in the system software or programming environment? So, as you think about creating monitoring tools, is trying to help kind of answer some of these questions. How can we take the information in the monitoring tools and make it so that maybe a user could answer some of these questions in their daily HPC clue playing and save some of their time. So I just wanted to share, to kind of really hit home how things are really integrated and complicated. I just wanted to share this one case study with you. This wasn't completed, and it's, we're still speculating. But it was a case study on Trinity. So during the early user phase of Trinity KNL, Sparta, a code from Sandia, authored by Stan Moore, was killing nodes, but only at a particular scale. So at greater than 2,000 nodes, KNL nodes would it's not just the application crashing, it would kill a node. And so we spent a lot of time debugging, trying to figure out why this would happen. Mike Davis is awesome if you ever see him from working at HPE. But we were able to get to the point where we could identify the point in the code, but not why the code was actually causing nodes to crash. And so, the only way to move forward was a workaround that Stan put in, and then I think the code was working. And that's disconcerting that we never was able to root cause this issue. And so a year and a half later, we had a summer student, Ben Burnett, under the mentorship of Dave Rich and myself. So we got to kind of look and say, what did happen? And so this is some preliminary results on some work that he did where we looked at, so the first graph is where we were looking at Sparta, and we had to do this at much smaller scale, so we can never actually kill a node. But we were trying to see if there were signatures of why maybe a node would want to crash. And so the first graph here is temperature in the red and its relationship to the system fan on the right. And so you can see that the system fan was connected to the temperature. It would turn on because the temperature went up, clearly. The second graph was showing how system temperature in the red was related to CPU utilization. So we see the percentage. And the thing to note is that there's these lags, right? So system temperature goes up and then fan turns on, but there's a lag. It's not like anything can happen instantaneously. Same thing with the CPU utilization. It went up, and then the temperatures would also start increasing as well. And then, the fans are turning on and things of that sort. And so what we were seeing probably on the third graph was that the way Sparta was running using Cocos, it had these spikes in how it would use the CPU. And so the temperature was not triggering the fans fast enough because of these very rapid cycle changes. And so what we think was happening was that the nodes basically, because of the temperatures, were dying. That's us, kind of speculating based on some of the data. But we would love to have real data, real time, at the large scale, so that we don't have to make these speculations, and then we can find these correlations, and later on we can then go back and inform to the vendors, hey, maybe the temp, the fan being turned on should not just be, solely tied to the temp. Maybe we should be looking at CPU utilization and things of that sort. So we would love to solve these types of mysteries, and we think the effort of monitoring is just awesome, and can't wait to get our hands on it. Thank you. I'm gonna stop sharing.
Great. So let's move on to our next speaker, which would be Richard.
Hi, great. Let me find the mute button and then I'll share my screen. Okay, hi, I'm Richard Gerber from NERSC. I'm the HPC department head there. And so I had just put together a presentation with just a few words to explain what I'm interested in terms of this monitoring effort. So all the things that have been described so far are fantastic, and I'm interested in those as well. But my personal interest really is in trying to understand the NERSC workload. And by that, I mean, understand the applications that run on our system and the users and how they use them and how they interact with our system. So just to remind you, NERSC is the Mission HPC Center for the Office of Science. So the Office of Science, many people don't know this, is the largest funder of physical science research in the US. And here's the areas the Office of Science is interested in. We have lots of users, thousands, approaching 10,000, there's probably more like 8,000 this year, approaching 1,000 different projects. More codes than we can probably count. So we have a very wide funded and users get to our center. I look at our workload as really characterizes the entire Office of Science community. And given the role the Office of Science plays in physical sciences, at least in the physical sciences in the United States, our HPC workload, I think, is highly representative of what is going on across many disciplines in that area. And so trying to understand what's going on, understand the needs, how they use the system, et cetera, is really interesting to me. And so here's the one slide about our goals. And I put the word entire up there, which wasn't there before, to really emphasize that I really want to understand not just what a few codes are doing, but really what the entire enterprise is doing on our systems. So what am I interested in? I want to know, well, at a very base level, what codes are running. So this sounds like a very kind of level 0 bit of information, but it's really not one that's easy to answer. So how do you think about how do you know this? Well, you talk to people. Well, if you have 10,000 people to talk to, you're kind of very much biased towards the few that you do talk to. So this is something that we have to learn from inspection in a certain way, because we can't ask them. I mean, we do ask them when they apply what codes they're going to be running, but we often find that when we actually look, it's something else. And they say, well, we changed our plans, or this came out, it was better, we plan to do that, we're not doing that. And so there is quite a significant difference between what people tell you they plan to run and what they do actually run. And what libraries and tools are they using? We don't have any, again, you ask yourself, how do you know this? And the only way to look, and looking is hard. So how, and in addition, how are the system features being used by our workload? How is IO being used? What's the memory bandwidth of the entire workload, or there's subpopulations within the workload that have different characteristics with all these things. And then, just who are the users in the projects? And so the demographics and tying demographics to characteristics of codes and how they're using things is interesting. So what would you use this information for? A lot of this has been mentioned already. Informing ourselves and funding agencies what codes, libraries, and tools to support. so you can have a great code or a great library or some great tool that maybe is the best ever written and would solve everybody's problems. But if in fact nobody is using them, we want to know this. And so then you can ask yourself the question, why aren't they using it? Well, maybe it's just a matter of education and evangelizing about the thing, which could add a lot of value if you got people using a really super tool that no one was using. But we want to know whether people are using it or not. We use this information to optimize system queues and configurations, provision services, whether they are edge services, maybe quality of service that you might provide for a system for certain jobs, educational services, outreach services, all that sort of thing. Of course, designing future systems based on that, what the applications are doing. If we're really moving to extremely heterogeneous type of systems, being able to identify portions of the workload that can take advantage of, say, different kinds of accelerators, different kinds of IO systems, different kinds of, it's that whole system balance and what it's made up of question. Optimizing debugging applications, you can often tell a lot about how well applications are using resources, as well as spot errors in codes. For instance, if you're able to look at how memory is being used by a code and you see a ever increasing with time memory usage, maybe this code has a memory leak. I mean, so very basic things like that could be useful. And then in addition to monitoring, so I don't like that word in general, but there is a monitoring component to this, is that you want to make sure while you have a system in production and operation that the applications continue to perform at the level that you expect. And if they don't, there could be many reasons. It could be the application, it could be the system, but you want to know that and be able to measure it. And I do want to say that we're doing other things at NERSC, of course, in terms of monitoring systems to help operational aspects of it, like temperatures and environmentals and things like that. And I'm not talking about that here. So we could get a whole different talk from a whole different group of people on that if people are interested someday. So one of the big challenges, and there's lots of them, is basically nothing was designed to make this easy. There's no good way to tell what code is being run. I mentioned about talking to each one individually. The libraries and tools generally don't log their usage, or if they do, it's not in any real kind of consistent way. We all know the hardware counters seldom tell us anything that we want to know, or make it really hard to even find out about, say, flops or memory bandwidth or something like this. It's different for every processor. It's different. It's usually some combination of different kinds of counters that may or may not be executed under certain circumstances. So it's not easy necessarily. There's really no standards in this area. There's very few tools that I know of. And it can be a huge data problem for systems at scale. So I just picked a random day in January and looked and saw we had 35,000 SRUNs. So if you know Slurm, you know what that is. It's an execution of something per day. We have 12,000 nodes. We have hundreds of metrics that could be collected and are being collected. And for doing that at a hertz on every node, it quickly becomes a huge amount of data. And the data problems are large in terms of volume, but they're also difficult in terms of, if you think about each data set that you might collect from some counter or whatever as a database, if you know anything about databases, you have all these collections of data and they often have very obscure or non-existent, think of foreign keys. So joining these is often a Herculean task in and of itself. So we're doing some questions, talk about what's working now. At NERSC, we have had a lot of success with Slurm logs. There's a lot of information in the Slurm logs, and Slurm is nice because we could in principle make our own modifications, but we also work very closely with Slurm developers. And so it's possible at least to get things into the logs that we don't have and that we'd like to have. LDMS has been really great. You heard talk about LDMS a minute ago. We're using it a lot. And that combination has allowed us to answer some specific questions. So people have written some very nice papers based on this capability, but in general, it takes a lot of effort to get it. And so we want the ability to make ad hoc, quick queries quickly to find out things. We've also been putting things in Elasticsearch and SQL databases for future queries, so we don't have to stress, say, the Slurm daemons and things that are currently doing other things. So the general state of affairs at NERSC, again, is LDMS is valuable. There's challenges, data management, and the performance of the analysis, like doing essentially those table joins and all kinds of other things, and dealing with file formats and our major issues. Another thing that's been a major issue is validating the data that we're collecting. So, a simple example is something like SORM will tell you some things like for every S run, the maximum memory that was used across all nodes and ranks. But if we're using that and then we start looking at it in a little bit of detail, it quickly becomes obvious that some of the numbers are clearly impossible numbers. And so, how do you deal with that? Do you throw away the obvious things? It makes you really question and have to do a lot of deeper dive into validating whether any of the numbers are right or just some of them are wrong. And anyway, there's lots of little screwy things like that. Like some of the logs, even within the same logs, some fields will have UTC and some of them will have time zone adjusted times. So there's these little things that you think should be minor annoyances can be real headaches when they pile up in numbers. And then there's no real go-to visualization tools that people are using that I can tell them. So what could we improve on in this group? I'd say setting up best practices for configuring LDMS, data management backends, analysis tools. It would be great to be able to share things and see what's been successful for people. And we're doing some of that today, so that's great. But even simple things like, what's a good sampling rate that was mentioned earlier? There seems to be this default 1 Hertz rate that people choose, and I always question why. What's so special about 1 Hertz? It produces lots of data, but from a processor clock perspective, that's there's a billion clock cycles that have gone by. So would 10 seconds work? Would 100 seconds work? Do we need millisecond? Those kind of questions are interesting, and having other people's experiences around that would be helpful. And again, what metrics are useful for what isn't. The default configurations, say in LDMS, collect all kinds of counters, gobs and gobs of things, most of which we will never going to look at. But yet they're there and we have to deal with them in the data management standpoint. So we're probably better off turning them off, but which ones are the good ones to do so? Can we have a common set of languages or metrics to compare workloads? It would be interesting, I think, if we could put up some kind of simple graphic that said, here's the workload at NERSC, here's the workload at Oak Ridge, here's the workload at LAML, and here's how they differ in some various dimensions of interest that we could all maybe agree upon. Of course, it's always a challenge to identify the individual applications. How do we see in the logs that something called PWX was run, and we have to know that I think in that case is quantum espresso, but it's one of those, it's some electronic structured code. And then can we convince application software tools or whatever developers to log their usage in some standard way? I'm not sure what I meant by performance measurement, or maybe write them to LDMS or some way that we can get to them and associate them with the different applications and with them. Things that we've tried done, we take the SORM data and put it into a MySQL database or Elasticsearch. So we can do queries after the fact, and maybe very CPU intensive queries that won't perturb the running SORM system. We've been looking at post-processing LDMS node-based time series data and associate them with the job IDs in Slurm and saving them in these Parquet files that allow us to access the data much faster. We're also doing the same kind of thing and putting in an SQL database so we can query things much faster. And we have a whole set of Python routines that go and find the LDMS data that's a time series associated with jobs, and then we associate that with known applications based on their binaries names, which is highly imperfect, but it's kind of the best we could do. And that's it. So I've mostly described a lot of challenges. I wish I had more results. I will say that we are making a lot of progress on these challenges in terms of data management, and validating that the numbers in the files really are what they think they are, and that the units are what we think they are, et cetera, et cetera. So hopefully a year from now, I'll have some better and more interesting results to report, but we're still not there yet at NERSC.
Okay, well, great.
Thanks.
Richard, another wonderful talk. I've loved all these talks so far. Let's go on to Bill Kramer now to conclude the talks, and after Bill, we'll transition into an open forum to have a discussion period. So Bill, take it away.
Okay, everybody. I assume you can see my slides on my screen. Happy afternoon. I'm going to be talking about what we do at the University of Illinois, and particularly about the Blue Waters Project. We'll talk a little bit about some of the...
Bill, we can't see your slides.
Oh, okay.
You need to share your screen.
Thank you. Let me try to do that again. I thought I had. I see the problem. Is that better?
Yep.
Okay. So let's move on for the sake of time. A slide of introduction. I'm not going to go through these slides in great detail. Blue Waters is a very large CRAE system. It is an NSF system, so it's not a DOE system. And it is about 45% bigger than any other system CRAE's made. The next biggest one was Titan, and we've been in service since 2013 and still continue service. It turns out to be a very reliable system. We supported all types of ranges of science and activities across the first 7 years, and now are specializing in more geospatial geointelligence activities. Blue Waters has about 27,000 nodes. A significant number of those have GPUs, and the rest are all CPU nodes, and you see the details there. Again, I won't go into it, just to take away a very large system, and it needs to be evaluated and assessed, both from the application side of things, as you've heard, and from the system side of things. So the motivation for what we did to create the monitoring infrastructure, which was developed in conjunction with the deployment of the machine, is to do things like the graphs on the right. The graphs on the right are showing two different applications. They both run at substantial system size and showing the differences in their behavior with some metrics that we collect using Ldms. In particular, on the left, it's the messaging that is going on from the interconnect NICs, in showing different patterns between two applications, and these are on normal use. So we start from that, and wanting to understand these patterns, and then we'll move on to some of the other things. Our integrated system console, which has evolved over time, takes in basically any data that the system can produce, all the node and NIC performance counting information that Ldms very efficiently passes, as you heard Ann talk about, job and application scheduler information, library usage, all the storage information from our large file systems, event logs, notifications, alerts. It all flows into a set of databases in a single system after being parsed by a variety of different tools, and then becomes available for multiple ways of use of this system, ranging from tools that we have on websites for our support staff to understand what's going on, and we actually provide some of that to our users, the people who run the applications, our facilities information, temperatures, power, things like that. We also do notifications. We have console panels, which are essentially dashboards. We are able to do in-depth research and analysis of, say, multi-year workload studies that we've done, again, with the same set of information in different ways. And then visualization, both on our out to the public about what's going on, and then to our staff and users. So many different purposes. The metrics we collect are node metrics. You've heard some of those, but basically a large number of node metrics, flop rates, free memory, GPU utilization, file systems, what is read, written, all the metadata activities on those file systems, each interconnect NIC, the bandwidth, the use, the packets, the stalls, whatever, for understanding what's going on, library usage, and then MPIAO operations using a tool called DAWSHAN. These all flow into ISC and then are available for understanding. As was mentioned, ISC supports SQL queries, file dumps, web interfaces with dynamic real-time visualizations, long-term analysis products and reporting, the dashboards, and actually publishing the data sets, which I'll talk about at the very end. There is no system or performance impact. We've studied this, and there's some papers on it. We know at scale, we don't introduce any jitter to the highly parallel applications. And most of the performance impact is none to negligible, including the tools that we use for collecting the IO performance. So it's very efficient. So what do we do with this? I'll give you a few examples quickly. Here is one example of looking at a particular job. This job was identified and running a long time, and our support staff looked at this job. It was using 22,000 nodes, and it was an application that had one MPI rank with 32 threads per node. So if you look at the graphs on the top, and I know they're a little hard to read, the red is the CPU usage of the system, and what was first observed is it's computation intensive for about the first third of the time period it's running, and then computation drops to 0 for a long time period, and then has a little bit at the end. You see the CPU flops on the top left. So that made us curious. We looked at the node data, the IO it was doing, file systems, whatever, and identified two problems. First, the code was overscaled. It didn't need to use 22,000 nodes, and it ran out of work with the problem that they were solving. But also it was using a home file system, which is about 1/10 the bandwidth of our scratch file system. So as it started to clean up and summarize, it's taking a very long time to do that IO. We contacted the user. Again, this is something that there was no profiling, there was no anything that the user did with the code. We just went out and looked at what the code was doing with our metrics and identified the user, contacted them, and within a very short time period, things were adjusted. And now the code runs in about a third of the amount of time to do the same work. And the other benefit is because it was using almost the entire system, now the system is available for other work to be done while still the productivity of this science team is not impacted, as a matter of fact, improved. Another example is LS-DYNA, looking at different phases of that run. And you can see that we can identify the different types of routines that are being used at different phases of the node run, just simply with the profile that we record on a regular basis with that. We also look a lot at congestion in our networks and our file system, and that chart on the bottom will actually be dynamic and show how congestion changes within the interconnect, and then we're able to look at influences, or is that coming from the interaction of applications amongst themselves, or is it coming from something else, failure rates. Here is another view of the Sparta code that you heard about a little bit earlier. We were asked to look at that code also and see if our production monitoring would be able to help understand a performance issue with it, basically low poor performance at scale. So we took the code. We had no background in using this code, but we put it on Blue Orders, and with no modification, only a recompile to make it work in our environment versus the DOE systems that it ran on, and no knowledge of Sparta, we non-intrusively were able to monitor the code with our standard measures. You see some of the graphs there, the CPU utilization, the relatively low amount of that, the imbalance, and then the graph, the third graph, the most to the right, shows the load on different nodes. And you can see a very large imbalance between every other node being low and high. So to get to the point where we had identified what the issue was and in the corrective action, it took us about 4 hours of a person's work using that without having any changes or reprofiling of the code. We're told that a similar, the original analysis took about 14 days of work in multiple runs to try to find out what the issue was. So it's an example of increasing productivity of the code, but also increasing the productivity of the support staff who are helping people become efficient and use systems well. What our work is now is trying to use machine learning and AI to help speed this up and be much more proactive. So the charts here are showing our work in progress to automatically identify similar codes or the same code running at different times, and then to look at the characterization of those codes to be able to enable us to compare and say, this code is running normally, or this code might have a problem. And then also determine by looking at system characteristics, is the system running normally, or is there some congestion or hotspot or something that would influence the code? We're doing this classification with unsupervised learning with very large data sets. It's the hard way to do that. We're not using what a system manager would use, which is to look at the code, the user, the project, the file name, and say, this looks to me like the same code. So what we want to do is use that as validation. And those charts are showing that, yes, we are getting good groupings of similar codes or the same code, the same user, or the tables there, and it's grouping and correlating these individual runs are actually associated together. And the table down below shows different profiles that now are coming out as saying, yes, these codes are similar. This works reasonably well for long-running large applications. The orange to the left are the short-running smaller applications where they're very noisy, and that is still a work in progress to do that. And we hope very soon to try this on DOE workloads. So as a summary, we no longer think of this as monitoring, which to me is a passive term, but it's continuous assessment, both for reliability, performance, and understanding both applications and systems and how they interact. Our comments and experience show that system and application data should be automatically and continuously corrected. If not, you miss opportunities to deal with transients like congestion and why that might impact a code. It's not going to be able to analyze problems after the code run, but they're reported without rerunning things, and the system may be in different state, or other applications may be involved. And without collecting this continuously, then we can't tell the users what their application performance is. We don't want to require users to turn things on and off, except that we do allow them to opt out if they want to do their own profiling. But in general, our users don't do that any longer because all that data is collected for them automatically. It only makes sense to collect this data if you're going to use it. And I hope what I showed you was some examples. Those types of profiles and looking at the code we do every day. Our system and application teams look at that every day to understand what's going on. And it comes up in a very real-time, flexible format. Richard talked a little bit about trying to use SQL and other things to pivot your views. We believe you have to be able to do this across all your subsystems. So sometimes the IO subsystem is impacting what the computational system does. So you have to have this all in one ecosystem that integrates all the information together and gives you very quick real-time analysis to do the investigations. And I'll comment again that we think that the current generation of tools like LDMS are very efficient. They are the collection is pretty well solved for our standard systems, but doing the analysis and increasing productivity and insight is something that has a lot of work to be added to that. But I will say that I believe that we need co-design for future systems, for hardware and software, co-design for monitoring and assessment, because what doesn't happen as easily is actually having all this ability up front when systems are new. We want that to show up at the same time the systems are showing up and be well integrated. And also, as systems become more specialized in the future, we're going to have to pay attention to co-designing the abilities to do this type of analysis. But without this, we would have a much less proficient, much less productive system without these activities. So one last thing, all the data that we have from Blue Waters for 6 years now is published. You can go to the website on our portal. That's all the information we collected. So terabytes of information are available for that, and it's been anonymized. We also have reliability and repair information, which I don't have time to talk about for that. And I'll stop there and turn it back. Thank you.
Wonderful. Yeah, thanks so much, Bill. So now we're going to do a pivot and transition to a moderated discussion among all in attendance. And the person that's going to run that is Dave Montoya. So Dave, take it away.
Just a quick question. Are we going to continue recording during the open session, or do you want to stop recording at this point?
Well, I would vote for recording.
Okay.
Are there any objections to that?
I think I'm good.
Okay, hearing none, let's just go ahead. Take it away, Dave.
Okay, well, those were all, I mean, really good presentations with lots of questions and perspectives. And one thing that I'd like to note is we have these sessions, and we've been having monitoring discussion sessions for many years. And it's interesting to see as time goes on, there is a lot of sharing that actually does go on, and somewhat standards as far as tools and utilization. So I think there's a lot of good discussion going on and a lot of good sharing. So I think part of this is just to continue that and seeing if we can actually increase it any more than what it is. So anyway, to get started, we only have about 15 minutes left, and probably a lot of things to discuss. We had put actually kind of listed a lot of questions if we had a lot of time to kind of run over, but I brought those categories up, and I just kind of left them up on top. And for the most part, I'd like to open it up to see if there's anything specific that anyone would actually like to kind of bridge into right away, or wants to ask questions of some of the presenters to go in a little bit more detail. And then what I can do is I'll just fill in the notes in the appropriate little category that we've got here. So let's kind of open it up from that. And I think everybody should be able to not mute and just kind of bring it up. I'm not sure how the handshaking or the raise hand things work. So to start with, does anybody have anything they'd like to bring up? Okay, well then let's kind of dive into the, we'll chip away at each one of these segments and then have a little discussion on what may come up with them. So one of the categories that seem to be HPC centers, and that tended to be with what are the centers doing as far as monitoring, and most of the monitoring infrastructures happen at the centers, but it doesn't necessarily cover all the stakeholders in many cases and the users. So, you know, in our abstract for the session, we said the DOE computing centers track a lot of information. The question is, how true is this? How consistent is it? And who's the center collecting it for? What I heard, there's a lot of different targets that they're using. What Bill seems to have is a little bit more open scenario where you are sharing a lot of that information. It might be nice to have a discussion as to the issues of getting data to the right people, and is the right data there for people to do something with. So Bill, do you want to expand a little bit on how are you able to get that to everybody who needs it, and are they using it?
So we believe so. We have all that data available for our support staff. We don't automatically generate all that data or allow unlimited access to that from the user point of view, but we generate things for their own usage. The reason for that is simply we don't have the servers and databases performant enough for have random queries going on by lots of people. So we manage that a little bit, and that's a hardware-based limitation, investment-based limitation. But all the data is used by the staff. There's a lot of cooperation and collaboration between what does this mean? If you look in how the staff works together, the applications people, the systems people, the planning that we do, even the implementation analysis of when we went to topology-aware scheduling came out of that same data, and we were able to demonstrate that it was 40 to 50% improvement on productivity when we went to topology-based scheduling. So that's all there. The data release I talked about, we ended up taking a long time to anonymize the data. It's obviously a lot of data, but now that's anonymized, so people don't need IRB approval for looking at that data. And some people have started to access it, and we've done collaborative work so far, but other people might find it useful. It's a lot of detailed data, and the proper interpretation of it can be very subtle. So we find people may not be familiar with the metrics and the system to properly interpret it, but we work with them on that.
Okay, no, thanks. So comparing that to, let's say, the NNSA labs, and Jim, you're there. You and Ann have kind of talked about trying to get data out to everybody, and I think that the other labs have other constraints as far as data accessibility. Do you guys want to bridge that a little bit?
So I guess I'll say that we, yeah, it depends on which data. So for instance, things like log data can't just be freely shared. That we can share that after cleansing, but we can't make it just available all the time, because there's stuff in that data that, especially on systems that aren't open, that just aren't allowed to be shared with everybody. The system data in general on our restricted and open systems is freely shareable with everyone, and we have some dashboards set up that enable users to look at their jobs, both resources that their jobs are utilizing, and that in the context of system resource utilization. So I think our users are starting to utilize those dashboards. That's Grafana based, and getting value out of that. And I think where we are now is really starting to try to work more on the analytics side, including, as Bill mentioned, machine learning, but using more advanced analytics to try to identify as early on as possible when we have when we're encountering bottlenecks and slowdowns and things like that. So and that as we harden those things, are being rolled into our displays. So as Ann was showing, the information, both application and system information, we're trying to solicit. In fact, from this community, it would be great to know what kinds of things you would like to be able to simultaneously look at. So, do you want application performance and progress in the context of system data, for instance? Anyway, that's stuff that we do we share with our users, and we are starting to actually share that kind of information. We've gotten permission to release a lot of that to, for external research consumption.
Okay, so getting into the analytics a little bit, I mean, obviously you can only analyze the type of data that is appropriate for the analysis that you're trying to do, whether that's machine learning or anything like that. Is there is a breadth of data that is being collected? Are there gaps in the data that's being collected, or difficulties in actually collecting some of the data that's needed for some of the analysis?
So from my perspective, we're missing a lot with respect to application performance metrics that would be nice to have. I think with respect to system data, I think we're light on GPU information, and maybe interconnect information could be richer.
Yeah, the question of data, we largely are still, if not completely, operating on trying to make sense out of the data that exists, that, as I mentioned, wasn't designed to answer the questions. We're trying to answer questions using data that wasn't designed to answer the questions that we're asking in general.
So Richard, you're saying we may not quite have the data to be able to actually answer the questions we're looking for? Is that what you're saying?
Well, I'm not saying we might not have it, but it's not being collected for the purpose that we're trying to use it in general, right? And so we're trying to answer the questions that are interesting to us using the data that exists that was designed to be collected for the most part for something else.
Right. I think in general, we are collecting data that's available and hoping that it can be applied to answering the questions that we want answered, and there may be an impedance mismatch there that we still need to discover.
So currently working with what we have, in other words.
For the most part, yes. Now, it's true that if you get Cocos or Tau or Timmery or something, a tool that was designed to measure interesting things we're interested in, and they feed data to LDMS or something like that, then that's a different situation, right? So that's collecting the data that we're interested in for the most part.
Yeah. Okay. Now that sounds good. So because it seems like the analysis is the area where we're trying to get to, and having the right data. So it really goes back to the collection. There's a big cycle of collection, what's the analysis, and what are the issues we're trying to solve. We only have like 5 minutes, so do you guys really want to talk a little bit more about, now that we've got at least heard from different perspectives and different labs, do we want to try to actually put any plans together, or what do we do with this nice information that we've kind of found out today, or that's built upon what we already knew?
I think that's a really good thought, Dave. Why don't we try to come up with some next steps?
Okay. So obviously there's more sharing that can be done. The good part about these sessions is we catch up on our knowledge, because we go back to our holes and everybody kind of turns away for a while, come back out and find out, oh, this is happening here, this is happening there. So there's good opportunity for sharing. And we've been trying to create a good working group scenario. And I know Terry's done a lot just in trying to get a group of people and trying to have sessions like we're trying to set up to something for supercomputing, and really kind of transition into a little bit more on the analysis side. Any thoughts on that, or broader participation ideas?
And so I think one thing that would be productive we should talk about is, as we saw just from the presentations today, there's a wide variety of things you could do with this data, from what people call co-design to application performance, anomaly detection, basically debugging applications. and other things. And perhaps we need more focus, or at least a way to talk about focus areas so that we can kind of have more, what's the word I'm looking for? More common in-depth discussions around in certain areas. And that would also provide a focus for when we want to talk to different people who might consume the data or might support collection of the data or this sort of thing. For instance, I'm not sure I'm saying what I mean to, but for instance, if you had a focus on co-design, understanding the workload so you can design the next heterogeneous system, that's something that a lot of people are, of course, very, very interested in.
Yeah.
And so maybe having a kind of a breakout session around that topic, and then maybe a different breakout section in this monitoring area around, say, things like the great plots that Bill showed about how applications are acting strangely, as they run, to help optimize applications that have this intense period of CPU usage and then don't do anything for the next 2/3 because they're hung on IO or on a MPI barrier or something. Something like that would be another focus area. I'm sure there would be others too, but that might help focus the discussions a little bit and get other people more interested.
Yeah, I think, Richard, that kind of goes to the area that we had down here, which is who are the stakeholders and the users.
Right.
And really, I think like what you're saying is, if we carved out and defined who the stakeholders or user categories are, and then actually got their perspective, like Hea gave on from an application perspective, then we could actually start taking inventory. Do we have the data that needed to do that, or what is missing, or what is different about the type of analysis that stakeholder is doing? So that might be a good focus to start with.
Yeah, good idea. Well said.
Stakeholders. I think we've pretty much run out of time. So let me leave it here and pass it back to Terry. Terry, if you wanted to kind of close out, because I don't know whether they shut us down or not at the time.
Yeah,
I'm sorry we didn't have enough time, but
I don't know exactly how things wind down either, but let me just say that we do have this recording and I am saving the chat. So somewhere on the ECP website will hopefully be a link to where you can watch the recording. I have the chat saved, and I believe I've captured the names of most of the people that attended by looking at the participants panel. And I plan to send an email list to let people know that the video is available and that the chat is available. With that list, I hope that we can start an email chain on how we can work together and make some progress in this area, which a number of us see as important and with potential to really improve supercomputing. So with that, let me thank everybody and especially my co-host for making this presentation and the participants for coming and making it a good discussion. I